Thank you so much for that introduction, and thank you all for being here. So, in this talk, we're going to talk about web browsers. We do different kinds of computations. We use different tools to compute certain things, but one important thing that comes out to be is how do we deploy such tools so that people can use the software that we make, and what our deployment model could be. So in this talk, we'll be exploring how can we um, deploy things or whatever we make to web browsers or make the stuff more distributed, and we'll explore all new things that web browsers are capable of. So let's get started. We'll start this talk by seeing the current trend, what things do we use, and different kinds of tools and software that we use today. After that, we'll move forward to how do we distribute the things that we make and how do we deploy the tools that we make. Then we'll talk about a new compute surface that has been emerging these days, and we'll see how web browsers fit exactly into that model. After that, we'll see a few features of web browsers to support these arguments, and we'll see how they are actually capable of handling some of the advanced stuff that wasn't possible a few years ago for certain web browsers. Then we'll see how the whole ecosystem around web browsers is developing and supporting these arguments. After that, we'll stop talking into abstractions and actually see some statistics and some results and compare the performance that we get on different types of architectures. And then we'll see what's going to happen next and how our deployment models will be moving forward. So let us started with seeing the evolution of computing. So we started with the compute models of Z3 and ENIAC, where we had those large physical machines. After that, languages such as Fortran came into picture. Then libraries which were foundational, such as LinPack, BLAS, LAPACK, those come into picture. Then we had certain high-level environments such as MATLAB and Python, which helped us to abstract those details from low-level languages such as C. And then these days, we due to the rise of machine learning and deep learning stuff, we are again seeing increased rise of complex computations, and through that, we are having different things such as web native compute that is emerging. So this is the thing that we are going to talk about in this talk. So now, if you want to deploy the most basic application, this is just a very small example. What we do is we have certain client devices, smartphone, PC, laptop, or anything else. Through a network, we send those requests to the server. It sends a response, and then we get our results on our devices. And this is a very basic model, and it is actually a reasonable one. And it works really well when we have small kinds of computations, or if not small kinds of computations, if we have majority of tasks to do, this is a very good model. But what happens if the computations become complex? And what happens when we need to scale this model? Now, when we try to scale one such model, we see the addition of certain other components, such as we now add load balancers, we now add caching, we now add certain cloud storage servers, and we add tens of different things. So at this point, what happens is, irrespective of the nature of computation that we need to perform, there are tens of different components that add up, which are more advanced as compared to the computation that we need to perform. For example, you just need to calculate the absolute value of all elements in an array. That is not a very complex computation, but still, with the current deployment model, all these components will come into picture for even those small kinds of computation that you need to perform. And this doesn't make much sense for every time, or if we want to do it every time. And if we see some of the context in high performance computing as well, we have supercomputers, GPU clusters, HPC facilities, and facilities where we do centralized computation. And then in order to distribute the results or in order to interact with those computations, we can have even much more broader ways, which we will be exploring. So what happened in earlier days, and to some extent in these days as well, computation is tied to physical machines. And what we do is we submit jobs through maybe the client server model or through maybe batch schedulers, and then wait for them to execute and then gain the results back. But there have been attempts to make this centralized model more distributed so that we do not rely on one such computation center. And now the previous attempts that had been made to distribute the computation involve projects such as Folding at Home and City at Home. And what they did was they were a type of volunteer computing projects where, in order to run molecular simulations, people registered for these projects, and then these projects would use the idle capacity of devices of other people and then perform computations on their idle devices. So the main concept which was flowing here and in peer-to-peer distributed computing and grid computing as well to some extent is how can we harness the idle capacity of our devices. We have millions of devices and they are just sitting idle in our pockets or on our desks. When they are idle, how can we bring them into picture and use their capacity? And at this point, one observation comes that if we just need to distribute our computation, there is actually a better way to make it more distributed and to make sure that it reaches more people. There is one such platform which exists on not millions but billions of devices that requires no installations, no external setup, and that is basically accessible in almost all devices. So if we see these projects, such as Folding at Home, the main difficulty here was users had to explicitly install software, set it up on their devices, and then start executing them. And that led to a deployment friction. Not everyone would be comfortable in doing all that setup. And that's where web browsers come into picture. And they are the ones which provide these things to us. We don't have to install something. We don't have to manage external environments. And they are basically accessible to all of the users having devices that support web browsers. So now one more argument comes that, okay, fine, I can do the same computation in my servers as well. Why do I move my computation from the servers to the web browsers? One thing comes into picture is of privacy and security. When the computation happens locally, if me as a client is performing something and my data is not going to a server, I feel more comfortable using that application because the data is staying on my machine only and not going to some shady server. Second thing comes out to be reduced latency. The network latency is cut off in this picture, so there's not much time involved in going from flowing our data from this device to the server and getting it back. So network latency is reduced. Third things comes out to be that we now have a billions of distributed compute nodes, and each compute node here represents a web browser on a certain device. And the fourth thing comes out to be zero friction deployment. So if we are doing any computation on a web browser, a user doesn't have to install any explicit thing. There's no packages that need to be installed, or there are no external environments that need to be set up. Now let us see a few features of web browsers through which all this can be possible. And one of these is WebAssembly. And to give some context about WebAssembly, what WebAssembly does is, suppose you have your code in languages such as C or C++ or Rust. That code can be compiled into an intermediate representation, such as using something such as LLVM or any other compiler to compile it to an intermediate representation. And once that code is compiled to an intermediate representation, it is converted into a compact binary, which is a WebAssembly module. That compact binary is then read by the browser runtime, And the browser runtime here contains the engine for WebAssembly. Once that binary is read by the browser runtime, then it is up to the web browser to orchestrate that work based on the device on which that web browser is running. So if it's running on a laptop, it's x86 CPU, or if it's maybe on a smartphone, ARM CPU. So then it is the job of the web browser to decide how to orchestrate it based on the device it is performing the computation on. Then one more thing comes out to be something known as web GPU. So with GPUs, we have had a problem where in order to make optimizations, we tend to do vendor-specific optimization. So if you're writing code for an NVIDIA GPU or an Intel GPU, there will be differences. And there's no such methods that there have been certain attempts to, write vendor neutral code, but that fails many times. So what Web GPU does is it helps us to abstract out vendor specific details. So if you are a developer, you just have to write code for the Web GPU API, and then it is up to the web browser how to handle that code that you have written based on the device it is performing on. So the basic crux of this point is this thing. So now we have a hardware agnostic GPU acceleration where the optimizations that you make do not have to be dependent on whether you are writing it for an NVIDIA GPU or an Intel GPU or a Apple M series one. So then web browsers, they orchestrate the work through native drivers and the GPU. So let us assume that there is a web browser on my system. Now it is up to the web browser to decide based on what kind of GPU my physical device has, and it is up to the web browser to devise how to perform computation on that particular GPU. Now one more thing web browsers are capable of is doing parallelism. And suppose you have one main execution thread that can use different kinds of web workers which can perform certain independent computations on different CPU cores. Through this, parallelism also comes into the picture. Now there's one more thing web browsers are capable of doing is something known as web AI. So most of the AI tools that we use today, what happens is we send a query, the query goes to a server, and then we get a response. To decrease that friction, we can also do the inference locally in our web browsers. And many companies such as Adobe and Google are working on web AI where all inference takes place inside our devices. So then you don't have to worry about the data that you're sharing to LLMs or some AI tools, whether your data is being safe or not, because it is only staying in your device and the inference happens locally. Web neural networks are also coming into picture these days, and using web neural networks, your web application through WebNN API can directly communicate to the client's devices, GPUs or CPUs or accelerators such as NPUs. And this is a completely optional one. So if your client's machine doesn't have these GPUs or NPUs, it will just fall back to the normal cloud GPUs. Now let us see some high-level computing environments that we use currently. We talked about all the capabilities of web browsers, but let us see from a more broader point of view, how do we do computation these days, or specifically numeric or scientific computation. So we have these high-level environments such as MATLAB or Python or tools or libraries, whatever we say, NumPy, SciPy, R. What these do is they orchestrate optimized numerical kernels. So if we see, with the help of this picture, on the top we have MATLAB, Python, R, and Julia. Beneath them lie specific libraries with very specific implementations of certain algorithms such as BLAS, LAPACK, and FFTs. And beneath those libraries come the low-level actual implementations in C or Fortran or CUDA. So the productivity boost that we gain here is not because of performance. So it comes because of the abstraction that we make, and instead of working directly on layer 3, we work on layer 1. And it is this abstraction that gives us increase in productivity. Now, there has been an emerging ecosystem for web-based computation on web browsers, and there are many players coming into picture these days. There are libraries such as TensorFlow, stdlib, Transformers.js. Transformers.js is pretty exciting one because using Transformers.js, you can load a pre-trained model inside a web browser and then do the actual computation. We'll see certain demos which help us to visualize those in the later part of the presentation. Now, let us take an example of how an ecosystem develops for certain computing. And we'll understand this with an example of the Python ecosystem. So, at the base of the ecosystems lies libraries such as NumPy, and it is libraries such as NumPy which lay the foundation for high-level libraries to be formed on top of that. So if we have SciPy algorithms, or if we have visualizations using Matplotlib, and even above one layer of that, we have technique-specific things such as scikit-learn for machine learning and scikit-image for image processing. Then we have domain-specific things for astronomy, biology, and application-specific thing. So if we see all this stack that gets made up, the one thing that is the main part of it is the foundation that we make. And for any computation ecosystem to develop, the most important thing comes out to be the foundation that we are making, which was NumPy in the case of Python. Now, if we want to develop the same kind of ecosystem for web browsers, we again need this same kind of foundation. And in the context of web browsers, this kind of foundation comes out to be the JavaScript engine, the web browser, the runtime of the web browser, and libraries such as stdlib. So what these kinds of libraries do is, what stdlib specifically does, it tries to do what NumPy does in kind of Python ecosystem, making ND arrays, or through stdlib, by the way, you can also use ND arrays in JavaScript, and things such as basic algorithms to support the other domain-specific and technique-specific libraries that will be built on top of the standard JavaScript layer. So this is what is happening these days in the context of web browsers, and this is how an ecosystem is developing. Now, let us see what actually happens if we start treating the browser where computation can occur. We'll see a few demos based on the things that are talked about now. The first demo comes out to be object detection. We have seen numerous examples of object detection. Now the same object detection can be done inside web browsers. So there won't be any network requests going to the server to detect any object, and no such things. So if we see, this is an example of if we are using Google's media pipe, and this is live object detection happening without any network requests. Yeah, that can go pretty bad at times, but the basic idea, stays that we can actually do it. So the second demo comes out to be gesture recognition. I hope this works well. So yes, so what this does is it detects the gestures. So thumbs up. Yes, this works pretty well. So all this is happening directly inside the browsers, and there are no network requests going to any server. Now let us see how other ecosystems are also adapting themselves to work in the web browsers. So if we talk about the Python ecosystem, they have been using something called as Pyodide. And what Pyodide does is it uses WebAssembly to run Python code inside the web browsers. So web browsers run JavaScript, we all know. And what Pyodide helps us is using WebAssembly, it allows us to run Python code inside the web browsers. And same is what WebR does for R. So both Python and R ecosystems are working on it to bring those computations into the web browsers. And one main thing that comes out to observe in these cases is what these two kinds of environments do is they run an external environment inside the web browser, such as the Python runtime or the R runtime. They try to run those runtimes inside the web browsers. But instead, what will happen if we directly perform the computations in a language that web browsers natively support, that is JavaScript? So what I did was I made three different projects where I tried to do the same kind of computation, where I did a same image processing task to invert the colors of an image. The first example was where I tried the typical client-server architecture, where we were sending results to the server from the client, computing there, and then getting the results back. In the second one, what I did was I tried using Pyodide, where it used Python runtime inside the web browsers and then performed the computation. And in the third demo, I used JavaScript libraries called stdlib to do the computation directly in JavaScript. And here are the benchmarks if we see. So this is the picture. This is the operation that I did. This is a basic inversion operation. And what we see is, if we see the time taken by client-server model, which is around 3 seconds, and if we compare it with the time taken by Pyodide, which runs Python in the web browsers, which is 46 milliseconds, and if we compare that with the time taken by, if we compute it directly in JavaScript, which comes out to be 10 milliseconds. And if we plot this on a chart, we get these results. So on the x-axis, we have image dimensions on increasing size, and on the y-axis, we have the time taken. And if we see the client-server performance, that is not because our computation is happening in a bad way. That is because the network round-trip time is taking way too long than the actual computation is required. So this is what I talked about in the beginning of the presentation, where we have tens of different components, but the underneath computation is pretty fairly simple. And that's the difference that we get to see if we compare this client-server model with Pyodide or stdlib. Now, yeah, before finishing up, I just want to give one more example of one fundamental shift that can happen, was that our training pipeline, if we want to run an AI model, if the training pipeline remains the same, we train our models on our servers, we train them on our GPU clusters, exactly the same. What changes is how we deploy it. So if you are using it as a user, you are not sending your queries to the AI model that is deployed on your GPUs. Instead, that will be loaded inside your web browser, and you are just querying an already loaded model inside your web browser. And that brings us a lot of benefits that we talked about previously, such as data privacy and low network latency and all those stuff. So with this, I want to finish my presentation. And thank you so much for listening to me. And if you have any questions, if we have time, we can address those. Yeah, sure.
So one of the things I was curious to find, I know one of the biggest bottlenecks currently with web GPU adoption is transferring data, like marshalling data between the WebAssembly side and the JavaScript runtime. What work is being done currently to improve the latency of data transfer between the two?
So the main thing that we are talking about is the network latency that we are trying to decrease here is the network latency that occurs when we are sending our data or any query from the browser runtime to the server. The web GPU works inside the browser runtime. So the network latency over there is no network latency involved. There is a latency, but that doesn't depend on the network. That depends on your browser runtime. So we do not need to decrease that. because we are decreasing the latency for the data to go on servers and not the intercommunication between WebAssembly and Web GPU inside our own browser runtime.
Okay.
Yeah.
Hi, nice talk. I'm wondering about the distributed part, and one critical part of distributed workflow is you may have different communication patterns, point to point or all to all, or yeah. I'm just wondering how do you have that in?
You are talking
this?
about this one or this one?
No, for example, like I have 2 laptops and 2 brother sessions, and how do I really have a distributed computing workload running in these 2 sessions and have them communicate together?
So you are talking, you have 2 web browser sessions,
Yeah.
and you want intercommunication between those 2.
Right. Is that supported? Is there any library supports that? No.
Not in my knowledge.
Okay. Yeah. Thanks. Yeah.
I guess our HPSF board member Excel can't come. Sorry, it's CR-based indexing. Thanks so much for the presentation. It's super cool. I understand the WebAssembly, and I used this before. You can pretty much also vectorize down to the operations there. Is Web GPU also something that I could compile to from like some LLVM intermediate representation, or is this only a JavaScript framework? Because then, if it would be possible, then we could, for example, write a Cocos backend for that, and then could bring it to a lot of codes.
I'm not very sure about this, how you can compile something from an intermediate representation to Web GPU. That is something that maybe you can use it based on, so Web GPU provides a common API, and using that, you code for that common API, and then it's up to the web browser to how to handle it based on the vendor. So it does compile, it might compile it after how it orchestrates the task to the web browser. So what you need to worry about is just how to write it for the Web GPU API and not for any vendor.
Okay.
Yes.
Okay, cool, thanks.
Yeah, thank you. Thank you.